welcome to this podcast from the BBC World Service. Please let us know what you think and tell other people about us on social media. Podcasts from the BBC World Service are supported by advertising.
You know, in life, no matter how much you are down, if you are willing to give your best and fight, you know, you can always have a fighting chance to come back.
We had to rise from the ashes.
Search for amazing sports stories wherever you get your BBC podcasts.
Welcome to Science in Action from the BBC World Service with me, Roland Pease. Later in the programme, a storm brewing over the controversial idea we should have a geological epoch named for today, the Anthropocene. I'm talking to one of the proponents what the argument is all about. Also, some delightful natural history, the cleverness of bees.
One of the things unique about human culture is that it's by nature cumulative. That in the past was thought to be unique to humans, and this is the first time that it's been found not just in insects, but to my knowledge in any animal.
And also the loving, nurturing care in the soils of Brazil. A kind of milk, but not from a mammal.
The milk, recognize it by the fat and the sugar. And it is more or less is close to the mammalian milk. You see, the animal adapted and changed all the body, the way that they take care of the children. This is fantastic.
But what better to light up the start of the programme than the first stars in the universe, made of the pristine stuff of the Big Bang, a real let there be light moment. Of course, they are far, far away. None has survived until today, but not so far that the new James Webb Space Telescope can't catch a glimpse. And a team of astronomers scrutinising pixelated images of a primordial galaxy near the edge of the visible universe think they've seen some of that critical first light swirling at its edge. One of them, Newton Fellow Hannah Übler, told me they could be the start of a journey that led to us all.
I think one of the ultimate excitement about the first stars that we think that these are really the first sources of light in the universe. So these are the first objects that produce light, and this light then starts to light up the cosmos, let's say. So this not only has the visual qualities that we know from light, but also these photons from these first stars, they start to influence the whole universe.
And they're made, as I understand it, I mean, it sounds recent, from the pristine stuff of the Big Bang. They don't have all the sort of the crud that's been made in an earlier generation of stars.
Exactly. Just as you say, they are made out only of hydrogen, helium, and very, very little amounts of heavier elements that the astronomers call metals. And only through their life cycle and then later explosions of these stars, the heavier elements are produced that, you know, you and I and everything around us is made of.
And so you've been looking at this. Well, I've looked at the map, the image that you have in your paper. This is the faintest smudge of light that has been picked up by the James Webb Space Telescope. It's sort of a few pixels of quite bright stuff, but you've actually been not even looking at that bit which is the middle of a galaxy, but out at the edge in what looks to me like complete darkness.
Yes, these are incredible data. So as you say, primarily we were targeting a galaxy called GNC 11, which is at redshift 10.6. And so for being so distant, so it's in the very early universe, is actually relatively bright. One of the brightest objects that we've known so far, that is so far away from us. But as you say, we then discovered in the observations this additional cloud of light, which in some of these filters, we cannot even see anything, but this only comes through in one specific emission line, which is the helium-2, which is one of the signatures that people are looking for in identifying the first generation of stars.
And as I understand it, the light you're capturing isn't directly from the stars themselves. You're seeing the way that light is sort of filtered or interacting with the gas in the surroundings of those stars. When you talk about this ionized helium-2, that's the the clue to everything that you're sort of building this story on.
Yes, exactly. So in trying to detect the first stars, as you've already mentioned in the beginning, we think that they are only made out of hydrogen and helium. And so seeing a signature of this helium-2 in this case, so it's doubly ionized, this requires a lot of energy. And this is one of the signatures that people are looking for, to have a very strong detection of this. And this could be directly from the stars, or could also be that the stars are sort of lighting up the surrounding gas, and we see a signature from this, basically.
I mean, what does it tell you about the stars, then, that are making this light? Can you work out things like how hot they are, how big they are, how vigorous they are?
Yeah, so from these observations, we were finding that the mass of this putative clump of first-generation stars, or first stars, is relatively massive.
Give me an idea what you mean by high mass.
Yeah. So we constrain from the light that we see there a mass that is around a few times 10 to the 5 solar masses.
A few times 10 to 5, sorry, a few 100,000 solar masses.
Yes, so it's a lot, okay?
And that's how many stars, do you think?
So we don't, as I said earlier, we don't know exactly what is the mass distribution of this first generation of stars. So for sure this is a cluster with several stars, but how many exactly these are, just from these observations that we have here, we cannot tell. However, we've applied successfully for more observing time, and some of the data that we will get there will hopefully help us to pin down a little bit more what could be the masses of the individual stars themselves, or also whether this could be a potential different, another very exciting scenario, which would be a direct collapse black hole.
I mean, you said that this clump is, even though it's the faintest grey smudge on your camera image, you're saying that it's very bright. So, if it's a few 100,000 solar masses, what about the brightness of it?
Yeah, so they are extremely bright. If you were next to it, it would completely be blinding you. And if we talk about it in relation to, for instance, our own sun, which is what we understand a little bit better, then this is more than 10 to the 10 times this amount that the sun has.
10 billion.
This is 10 billion times, so it's basically unimaginable for us, yes.
I mean, so now it makes sense, so these stars must be phenomenally bright locally, presumably phenomenally hot, and that then goes back to what you're saying about how they start influencing the gas around them.
Exactly, so the fact that these stars are very massive and very hot means that they produce very energetic photons, so light rays, and so this immediately impacts all of the gas around it, and also we believe starts the process of reionization, which is sort of a phase change in the history of the universe that we also try to constrain through the JWST observations.
So this is a pretty critical moment in the evolution of our universe, and it's a few 100 million years after the Big Bang.
Yes.
And you're going to have another look. What else can you do to try and work out any more? Because you've already used it for several hours, the James Webb Space Telescope, to look at just this tiny object, as far as I can tell.
Yes, so we will get actually many more hours on this. So we have different programs coming up. So we have one program that was awarded just now, where we will get another 40 hours on this object. They
must really like this work if they're giving you all that time. Everyone wants to work with the James Webb.
Yeah, you have to understand that this is really enormously exciting, and the potential impact of this discovery would really be, a milestone. And so I think people appreciate that this is a very important and also very promising target to look at.
I don't know if this is a silly question. How similar is this galaxy that you're looking at to what our galaxy might have looked like 12 billion years ago?
So GNC11, when we observe it, is extremely compact. Just a tiny fraction of the size that our own galaxy has today. But just like, as humans, we grow over time. Also, the galaxies have to start out small, and then over time form more stars, and these galaxies will slowly but surely grow and assemble more and more mass, maybe also through mergers. And then at some point you get out galaxies like our own one.
But if I put it another way then, if there was someone on a planet orbiting a star in GNZ 11 looking this way, they might see what our galaxy looked like 12 billion years ago and be having a similar conversation to the one we're having.
Yeah, indeed. I think that could be fun, though we don't know, of course, how GNC 11 looks right now, right? So everything that we see is basically images from the past. And as you correctly say, they would also see sort of a baby Milky Way. So it could be an interesting conversation for sure.
Just get out that walkie-talkie. You must be so happy to have been, where you are in your career just as the James Webb Space Telescope was tuning up to do your work.
Yeah, this is really a fantastic opportunity to work on data that we never had access to before. So this is really, extremely exciting and very intense. And I'm, very happy and grateful that I can participate in this endeavor. It's really a fantastic time.
Hannah Übler of Cambridge University already working the data to find out more about those primordial stars. With confirmation that February was, for the 9th month running, the hottest month on record, heat waves across Africa, record temperatures in the oceans, melting poles, global CO2 levels not seen in millions of years, there is no doubt we are transforming the planet. And that's before we talk about deforestation, erosion, all the concrete, all the plastics. There's a name for it, the Anthropocene, the age of mankind, and there's a proposal this should be recognised as a real geological epoch, like the Oligocene, Miocene and Pliocene of past millennia. But the international commission responsible for such decisions just voted it down, and the latest reports are they did so controversially. Geologist Jan Zalasiewicz has provided much of the drive to name the Anthropocene, and he's on the line to share his thoughts. First, Jan, thanks for joining us. Why the Anthropocene? Is it important?
The Anthropocene matters because it describes the way the Earth has changed, just as you've described it, from a long period of stability in what we call the Holocene epoch over many thousands of years into something now much more unstable, climatically, biologically, chemically, even physically. So yes, it does matter.
And the idea is, in a sense, in a million years' time, a geologist might come along and they'd see it in the rocks that they looked at. They'd see that this has been transformed in the way that, sandstones and stuff of the past have been definitive of some kind of geological processes.
Yes, it will be very clear in the rock strata of the future. It is already clear in strata of the sedimentary layers that have accumulated over the last 70 years or so.
So you have been working on ideas that some kind of geological marker that would show where this era began. And it's things like, lead pollution or radioactivity are the kinds of things I think you've been looking at.
Indeed, there are very many radioactive markers from the nuclear tests for sure, pesticide residues, fly ash, the remains of invasive species. There are literally dozens, probably over 100 signals.
Going back how far?
The biggest change took place at the mid-20th century, something that's been called the Great Acceleration of industrialization, globalization and so forth. That's the best time to place a change between the time of the Holocene and the Anthropocene. It really marks a substantial change. Humans have altered the planet before, of course, for thousands of years, but humans have lived on a planet but didn't change it fundamentally. The difference now is in the fundamental change.
And this had got as far as a formal proposal to the geological congresses of the world?
Indeed, yes. There is an Anthropocene working group of the Subcommission of Quaternary Stratigraphy. They've been working for about 14 years and prepared a very detailed proposal to formalise the Anthropocene.
And so what is it that's happened this week or last week? Because I didn't even know that this was going to be formally considered.
A vote was announced, but it is problematic because it was not authorised, let us say, by me as chair or by a vice-chair colleague of mine who should have had the decision. there are a number of other irregularities.
And this sounds weird.
It's irregular. So I've just written a report as chair of SQS to the Quaternary Subcommission and the executives of the bodies above to suggest that this vote should be null and void.
I mean, were you told about this vote yourself ahead of time?
Indeed. It had been suggested by other members of the executive of the subcommission. I and the other vice chair strongly disagreed with it. We registered our disagreement. Nevertheless, the vote went ahead, with the results that you have.
I suppose what I'm sort of wondering is, you thought that there needed to be more consideration, or that you wanted to see a positive vote go straight through?
More consideration.
More consideration. So this has been rushed through, you think?
It's the Anthropocene is a very complex question. It's far more complex with far more data, new kinds of data, than in any other kind of geological proposal. And what is needed is open discussion. The proposal has not yet been openly published, and consultation with the kind of people who are affected. More work needs to be done. A proper, wide-ranging, open and openly recorded discussion. The question of the Anthropocene has been controversial. The disagreements, if you like, have made discussion process and the examination process more complicated.
I sort of sounds like a storm in a teacup. I'm surprised there should be so much vehemence on either side. And I'm just wondering, does it matter to the rest of us, or does it matter certainly to the professionals, that this definition is actually set when the concept of the amount of change we're seeing, as I described at the beginning, is clear to everyone? Is it something that matters?
I think it matters in the case that if you have a word and a concept, and the concept is important, like a change of the planet that we live on, then that word should be defined clearly and systematically, so it's used in the same way always. One way of doing that is putting it on the geological timescale. That fixes its meaning. If there are other ways of doing that, then that would be just as good. It's the fixing on the geological timescale that is trying first. The Anthropocene makes sense if you use it to describe these very recent changes, because that is the transformation. Words, terms and definitions should be precise, so everybody knows what everybody else is talking about.
You sound very calm for someone whose past 10 years or so of dedicated labour has been sort of stamped on. And I think that is your manner. You're very softly spoken. But have you actually, behind the scenes, been firing off emails furiously to try and get something done about this?
There have been a lot of emails going around, but we try and also to have them calm. We're aware that this is controversial. We're aware that people have strong feelings. We are aware that these differences are not always science-based. They depend on one's, if you like, gut understanding of the world that we live on. So we try and, as much as possible, keep things calm, focus on the evidence. I mean, that is the main thing. There is a report, hopefully to be published soon. What's important there is the evidence within it and the detail of how the world is changing and how that change is being imprinted upon geological strata forming today. So I think I would be happiest if we talked about the science rather than the proceduralities of it all.
Jan Zalasiewicz, Emeritus Professor of Geology at Leicester University. Thank you very much. These things matter because we share the planet with all kinds of wonderful living things, like bees, which do so much for us, pollinating plants and enriching the environment, and proving to be remarkably smart, despite their tiny brain size. A study this week has shown how they can teach each other remarkably complex behaviour that no single bee could learn for herself in her brief life. Hannah Fisher went to the labs of Lars Chittka in East London to see how they revealed this skill.
So we have several flight arenas, as we call them. They are basically little environments for the bees to explore and find artificial flowers of varied colors and patterns, and sometimes puzzle boxes. And in all of these they can find rewards, sugar water, very much like in natural flowers. And we essentially capitalize on the bees' motivation to look for sweet goods, for sugar water, and they're very flexible and ready to learn all kinds of things in exchange for sweetness.
I see, so you basically have kind of artificial nectar and you use that as rewards. And why bees?
They're amazingly smart, and they're, for us, basically models to explore just how much intelligence you can squeeze into how tiny a brain.
Lars and I then had a closer look at one of the flight arenas.
Oh wow, there's the bees with a glass tunnel,
exactly.
A little tunnel to another smaller box. And
on the right here you can see the bee nest. So you can see lots of bumblebees, with some of them with little number plates on their backs for individual identification.
Number plates like car number plates, but the bee version.
Exactly, little license plates.
What nice colleagues to have.
Well, they do sting.
Luckily for me, I avoided a bee sting, but only because they were all safely buzzing around inside their little containers.
Can I see the puzzle one?
Sure. Mm-hmm.
In Lars' most recent experiment, they used a very specific puzzle, which was designed for the bees.
So here's one of the puzzle boxes.
Oh, okay.
It was in the shape of a record player, with a big rotating clear perspex cylinder which had a retractable needle-like section on the side. On that rotating part was a red lever, and on the needle a blue one. And under the clear rotating part there was an obvious area of yellow sugar water, the reward. And this is where it got interesting.
This puzzle box is special because you actually have to combine two different actions.
The bees had to push the blue lever and push the red lever around to uncover that sugary water. However,
you can't use the red tab unless you first move the blue one out of the way. So there is a two-step action pattern that you have to learn. That is, first move the blue tab out of the way, and then, only then, are you able to rotate the red tab until you can find the reward. It is very complicated for an animal with a brain the size of a pinhead.
And too complex for the bees to solve on their own. So Lars and his team stepped in. They trained 15 bees to each solve this two-step problem to get the sugar water reward. These bees were the demonstrators. They were then paired with 15 observer bees who had never seen the puzzle and had never been trained. 5 of those 15 observer bees were able to learn to solve the puzzle purely from observing the demonstrator bees.
The bees there mastered a technique of this two-step puzzle box opening that was too complex for any one individual to ever figure out by themselves. But using social learning, they were able to do it.
So was this the first time that this has been shown in insects, that they can observe and learn from one another to have something that they couldn't have done via instinct?
It's more than that. So we have found multiple different learning performances in the past, including counting behavior, including recognition of images of human faces, but also tool use that they could not have done by instinct. They had to be trained with these tasks, and the novelty with this particular experiment was the cumulative nature. So this observation that they could learn something only by copying from each other, that was so complicated that they couldn't have learned it, figured it out by themselves. One of the things that have been thought to be unique about human culture is that it's by nature cumulative, that everything we invent in our generation builds on many generations of previous inventors, and we just add something on top of that. Neither you nor I, without instruction, could invent even something as simple as a match or a pencil. This key element that makes human culture special, that in the past was thought to be unique to humans, and this is the first time that it's been found, not just in insects, but to my knowledge in any animal.
So these clever bees could lead to a whole new appreciation of animal culture. Lars told me that the next step is trying to find out whether these bees actually show this cumulative cultural behaviour in the wild. So, the next time you see a bee flying past, take a moment to appreciate just how clever they can really be. Sorry, had to be done.
Thank you, Hannah Fisher, and thank you, Lars Chittka, bee behaviourologist at Queen Mary University of London. Details were published in Nature this week. And there were more animal surprises this week. Snake milk. Well, not quite snakes. These are snake-like amphibians called blind snakes, which live in the darkness of burrows in the soil of Brazil. And it's not exactly milk, though it's close enough. A nutritious secretion to feed the hatchlings from their subterranean eggs. This species were already known to be caring. David Attenborough and his BBC team had been to the labs of Carlos Jared in Brazil to film the hatchlings lick their mother skin for the series Life in Cold Blood. But then Carlos realised there was more to this species' nurturing behaviour than that.
This animal is like a tube, and with no eyes, no legs, and it's difficult to classify this animal, but it's a very interesting animal.
They're tunnelling through the soil, is it?
And they live inside the soil all the time, all the life. They colonize the underground environment. They have no possibility to have many children, many babies. And the babies that they have, because they have no eyes, they need the mother all the time till they would be independent.
And your paper has a picture of the mother with 10, maybe, tiny little wriggling worms, the babies, all cuddled together.
Yes, perhaps it's around 6 to 16 babies.
6 to 16 babies?
More or less this.
And they live together with the mother for how long?
I think this is 2 months, 2 or a little more. But they born very, very fragile. But till 2 months is eating the skin and eating the compounds of the cloacal aperture.
And this is the thing I find so amazing. They are being fed by the mother a kind of snake milk.
Yes, the milk, recognize it by the fat and the sugar. And it is more or less what happened in the milk of mammalian milks.
But this is snake milk.
Yeah. But not snake, it's amphibian milk.
Quite.
Because this is not a snake. But this milk is close to the mammalian milk. And the babies eat the skin.
They lick the skin.
We studied this skin in the microscopy, and we see that there are several droplets of lipids in the surface of the skin. With these droplets, they have proteins in the skin. The babies eat lipids, proteins, and carbohydrates. And this is important because we had great problem to believe that animal only eat the skin of the mother, because they are so active and so smart. We thought that the animal perhaps have another type of nutrition. The group of David Attenborough came here in 2007. They filmed these animals, and they give us the trigger for this paper. We are seeing that the babies passed many times around the cloaca.
This is where the egg came out of in the first place. Is this the oviduct?
Yes, the end of that. But we discover glands in the oviduct, glands that produce nutritive solution or milk.
The other thing you mention is the babies make a noise.
Yes, this is interesting. A sound like a beggar. The babies give it, please, mother, release your content of your cloaca. But this is important in this type of environment, fossorial environment, because it's all dark and no eyes, no nothing. The sound is important in this environment.
You must have been so amazed. This is a fantastic story.
Yes, very good. I love to work with this. The plasticity of the evolution. You see, the animal adapted fossorial environment and change all the body, the way that they take care of the children. This is fantastic. I used to say that this type of animals is a little surprise box because this type of environment they live.
Wonderful life, well worth preserving. Carlos Jared is at the Instituto Butantan in Sao Paulo, and the details were just revealed in the journal Science. This is the programme Science in Action from the BBC World Service. I'm Roland Pease, and I'll be back with more science next week.
Hi, I'm former Wales international footballer Robert Earnshaw, and in Copper Bullets, a new 4-part series from Amazing Sports Stories, I'm exploring how my birth country, Zambia,